So just set this to record, and little by little, I hope, get better and better feelings of what this is all about, the probability story, I mean. So quiz was referred to exercise number 11, where we had total of 25 entries, and 6 of them were defectives, and then 19 remaining were good. I created a little question to find the probability that we had 2 defectives, which actually means that also you need to have a few good ones, since 6 were selected, then 4 remaining were supposed to be selected out of the good part. So 2 we get out of 6, and then 4 we get out of 19. And we also notice that the total number of selections possible to get 6 out of 25 was some particular number. So that's something we did prior. So that was a number of combinations from 25 to choose 6. And we also did the product, because and means to multiply, of combinations from 6 to select 2, and combinations from 19 to select 4, right? So that was the answer to probability that they wanted. The probability is a fraction, so in denominator we get total. So notice that our total did not really care about order in which we select those transistors. So we just get some defectives and some not defectives, and that's why we use combinations, because we didn't order. When we order, we use permutations, remember? So either combinations or permutations. So out of this total that we select 6 from 25, I needed a special number of defectives, only 2. So 2 I pulled from 6, that's my numerator, and 4 I pulled from 9. And this could be calculated using our favorite calculator here. So I can go with the functions, right? Remember how we get those combinations? Some people wonder, where are they? They're right here. So you go to functions on that calculator, Desmos, and go with the combinations choice. So you can click on this combinations. Then I go back to main where those numbers are and start placing 6, comma 2, parentheses, times. Again, go back to functions. So we get those combinations. And get back to main. So I put 19, comma 4. So I guess I did this setting on the right margin, and all one needed was to practice finding those combinations in your calculators or in online calculators. So put 25, comma 6, and this will be the end of it, right? So 0.3282 dot dot dot. That's the result. So in this section, problems are not very pleasant, and I'm glad that you're working on those. The question was, how about if I do problem number 1 exercise now, and I will be gladly doing it for you. I'm glad that you care about these, because today's goal is to continue working on the next page of this section, and we'll just do a little bit more. The more problems we do here, the better, because I think the more comfortable you will feel about all of that. So let's take a look at exercise number 1. So questions here says there are 1, 2, 3, 4, 5 people, looks like, all been invited for a dinner party. How about that? I'm sure that's exciting news, right? So the question is, in how many ways can they arrive? So some people will say anyone could be on the first position, 5 choices. And then once, let's say Martha came first, then anyone from remaining 4 could be on the next position. Let's say Lee came second, and then remaining 3 choices for the next position, then remaining 2, and then remaining 1. So n means times. So it's actually 5 factorial, remember? Or you could also treat it as selecting all 5 out of 5 people and permuting them. So you could also say this be permutations from 5 to choose 5. So either way, you will get the same answer, which corresponds to 5 factorial, which is what, 120. So we can double check this right now, just for practicing using calculator's sake. Notice here's the permutations, right, next to combinations. Go back to main, and you choose from 5, all 5, and you see that indeed it is 120 or 5 factorial. So it looks like you can write the same thing various ways. To find 5 factorial is more intuitive, but we could just use the formula approach, just say, oh, from 5 we choose all 5 and we permute them because the order is important. That's actually what they're asking, in how many different ways they could be arranged when you enter that place. In fact, looking at what is given here, the names of people, names, already tells you that they treat them differently, not like same numbers or same transistors. So once you assign each of them name, it means the order, the position is important. So I'm glad that you are able to log in this morning eventually. That's good. So I'm looking at part B of exercise 1 right now. It says, how many ways can Martha arrive first and Armando last? So looks like we're now going to have 2 people out of this 5 fixed, and we are going to already assign Martha very first position. So Martha is gone, Armando is lost. So what remains is just 3 people. Please notice that these questions are not asking word probability. Probability is asked only in the part C of this exercise. So that's why one needs to be aware that sometimes you don't need to divide. So in other words, how many possibilities are here when Martha is first, Armando is last? Looks like we have to select permutations on these 3 middle ones, right? So permutations from 3, choose 3. And again, you can do it intuitively and see that this is 6, or you could put it in the calculator and get 6. It's up to you. Looks like it's a nice little practice. And finally, question part C says, find the probability. So now we're gonna need to get a fraction, and numerator will be our total. And notice the total number of ways to permute these 5 people will be 120. The denominator is always total, and numerator is what they're interested in, that part B stuff. So Martha is first, Armando is last, so we get 6 out of 120. Someone is Alex, I can reduce and write this as 1 out of 20, I can divide denominator by 6. But if you don't feel like doing all this arithmetic, remember, you could just put it all in the calculator. It'll take care of it for you. So 1 out of 20 or 0.05, which is same as if you get just 6 divided by 120, and that's your result. So answers should always be in either decimal or in fraction, which is in the lowest terms. And that's what we have. So let's turn the page and see there are just nothing else but more questions related to all of this in here. And they have various exercises that deal with cards and etc. So what I can do is clear everything that I wrote so you can make a picture. I know some people like to make pictures of this. So you can try a couple of problems from this group up to exercise 20 on your own, because the concepts start after 20, right? So you can get this page. Let me clean this. So I'm going to stop sharing and share screen again. And you can make a picture, because what I want to do is continue talking about chapter 11, but move a little bit farther into next section, because it just continues dealing with all of these probabilities again. So let me move to the next page. That's section 11.6, that actually talking about some formulas that we'll use quite often. And here they are talking about so-called complement, or the opposite for our probability. So what they do is they say that if you have probability of not event E, so they have a little special symbol. So instead of writing not E, they put that prime. Well, I guess in mathematics, they like to have some kind of shortcuts. But I don't mind if you just say not E. And not E will give you probability of complement. So for example, if you're looking at genders of children, say girl and a boy. So if we say 50% it's a girl and 50% it's a boy, 50, 50. So we have found probability of 1 and then subtract that probability from 1, from number 1. So if that's 50.5, subtract from 1, you get another 0.5, another 50%. I think it's intuitive, but let us do some problems that utilize this idea from the end of the section. So let me go back to. So I think this section nicely, logically continues the story that we just started. And that's why I don't think this is really a different section. These two could be taught simultaneously. So that's why I just moved to the next section. So we practice to do a little bit more. And let me try exercise that will illustrate this complement or not A. Let's see where they have those. So let's say exercise 13, looks like that's where all this not questions start. So let me do exercise 13 and so forth. So it looks like they are dealing with a table that consists of 3,000 people that like to go to the movies. And they broke them into 4 groups based on the various ages. So up to 24, the next category up to 44, up to 64, and then up to 74. So if you total the numbers in this column, in the column number 2, you will get 3,000. So they split the so-called sample of 3,000 people into age groups. So exercise 13 says, find probability that someone is not in the group 1. So actually not in the group 2. Well, the way to get someone in a group 2, which is from 25 through 44, will be to see how many we have in that group. And looks like it'd be 1,080. And it's out of total of 3,000, so I divide it by 3,000. So whenever we look for probability, we already know that we need to just divide total into the number of people that fit that particular description, which is age group 25 through 44. And I can get a calculator to get this 1,080 divided by 3,000. And you will ask me, Alex, why did you find this probability? Because they asking you not to. If you look at the actual question of exercise, problem 13, they say, find probability of not that. In other words, if you take this group 25 through 44, and then you put the complement like they do here. See this prime, this little symbol. Well, you could just subtract from 1 according to the formula above. So if you have 36% of people going to the movies, what about not that? What about the opposite? Well, it'd be 64% not from that group, the opposite. When you say, you know what, Alex, I could calculate that differently. And indeed, you could calculate this differently. You could see that number of people that do not belong to this category I circled in red. So you could just see how many people will be remaining and then add them all together and divide the sum by 3,000. So it could be alternative way to do the same problem. And I will never tell you how to do the exercise. As long as you do this right, it'd be fine with me. But I'm just showing you that this complement story does make sense. So if you decided to just see which categories we actually consider in here, not 25 through 44, but everything else, and design the fraction that I just produced in red. So if you add 900 with 840 and with 180, then you better get exactly the same answer. Let's check this out. Divide by 3,000, and yes, it is the same thing. It is 0.64. Let's see. Why did you do same problem 2 different ways? Well, because I just wanted to show you that it doesn't matter. You don't have to do problems 2 or more ways than 1. You just solve it and move on, right? But just wanted to show that this complement formula that we have above here in this corner, well, sometimes does not have to be used, but it is very popular, I guess. That's why I showed. So let's see what else is in this section. Exercise 12 also seemed to have a question in the complement format. I just noticed that part B is here. So this exercise is related to another group of problems. So this exercise is talking about probability that randomly selected woman 75 or older has a disease. So what does this mean? Well, let's read the question here and the actual information for it in this bar graph above. Please notice that we're concerned with women, so we don't need to worry about men here. And their equation is find the probability that somebody has a disease. Maybe I'll put D for disease. Probability that a person has a disease. So how can we do this? Well, looks like here's the probability. So we need to read this graph very carefully. And notice that the chances that somebody has such a disease in 75 or older will be coming from the top of this bar that corresponds to, well, it doesn't really touch 0.8. So what is this? 0.7, 0.75. Well, we can only guess, right? So we can approximate. So I think maybe 0.78 or 79. It's not 0.80, but a little less. And it's not 70, it's more. So it's pretty close to 80, I think. So I believe it's 0.78. If someone says, no, Alex, it's 0.77, I will believe you. So this exercise is not very clear. It's not as clear as the previous problem I did. So this is definitely not a good exercise for the test, but it is a good practice. So we read the graph. So it looks like in the part A of the problem, they asked in exercise number 12, what's the probability? And we use graph to make our guess to get the closest possible. Now part B here, that says, what's the probability that woman does not have that disease, which means it's a complement, right? So I must subtract from 1 the previous probability that I found. And it looks like we need to use formula here. So here's an example where you, it looks like you have to use that formula. And when you subtract from 1, you say that 22% or 0.22. So if 78% of women have that disease, then remaining 22% do not have the opposite. So complements are always either that or the opposite. So that's, I guess, a nice example. Okay, so how about if I try another one? Exercise number 16 here, related to the table. So I kind of don't like this graph because it doesn't give us clear values, right? So if you have this bar, let's say here, is this really exactly a half or maybe a little less than a half? So what kind of number is that, right? So it's not really something that I want to put on the test ever. But exercise like 16 will make sense because it gives you clear numbers. So it says movie goer is at least 25. What do they talk about? Well, looks like they're talking about 3 categories at the same time. So it's probability of at least will compose 3 groups. That'd be 1080, right? Or means plus 840, or means another plus 180. And this is all out of 3000. So we add everything that fits description, because at least means everything but not that. And now I can get the answer. So we got what? Well, looks like I can do analogous fraction to what I had in the previous calculation. So It'll be like 1080 plus 840, right? And then one more number I put in my parentheses, and then divide this by 3000. So there we have it. 70% will be at least that. When you say, looks like this exercises are nicer compared to my previous section, because in the previous section, we had this combination story, and that was a little bit less pleasant looking when you do the calculation. So I hope you will enjoy this section a little bit more. And that's why I actually decided to move to it. And I think you will love problem number 14 for a little quiz for today. How about that? So try number 14. And you can either use a complement or calculate it directly, because you already know that I just need the answer that you put in the chat. So take your time, calculate, and